My name is Mihai, and I work with Paula at a Romanian company that helped develop the software. And this is a short introduction in how to interact with TVB. Before I start showing you TVB, I want to remind you of our website. It was already mentioned, but I want to say some things again. On the website, there is a section that is dedicated to the software. Is that second tab over there? And I think you've already been here because this is the place where you actually download the software. So you go here and you choose one of the icons that goes with your computer. After you've done that, I highly recommend you go here to the help and support. Okay, there is no internet, but if you go there, you will get links towards our documentation. Please have a look at the documentation before you start interacting with the software because it is quite a sophisticated package. It has lots of screens, and if you're just starting to use TVB, you might get confused what you can do there. And on our documentation website, there are tutorials that guide you through the interface. Also, on that page, there is a link towards a Google group. We encourage you to write us any questions that you have there, to report bugs that you will find. And if you're about to start doing some project with TVB, we also appreciate if you just give us, introduce yourselves and say that I intend to do this with TVB, just so that we can know you and probably give you some hints and help you along the way. Okay. That being said, how to install TVB? If you haven't already done that, after you've downloaded one of those distributions, you get a zip file. And there's no actual installation step. You just have to unpack that zip file somewhere. And how to start the application. This is quite small. I hope you can see it. I've downloaded TVB here. And on Mac, there is this TVB application. And you just double-click on it, and after a while... okay. And after a while, TVB will start. You might get a security prompt, because this is not a signed application from the store, so then you have to do the Mac thing of right-clicking, opening it, and give it permissions to actually run on your computer. Okay. So how does TVB look like? It will start like this. If it's the first time you've opened it, it is a web application. It asks here lots of questions about how to set it up. Just accept the defaults. Click Apply. TVB will restart, and then you will be able to use it. As you notice, the interface is implemented as a web app. Why is that? It is because all of us here, I think we use TVB as a local installation. You've downloaded the package. But TVB can also be used in a centralized way. You can install it on a cluster, on a server. And then many people can use TVB only from the web interface. So this is why TVB is made as a web application. In case you want to use it centralized, talk with us. But for now, we all use it on our local machines. The first screen is a login screen. The default credentials are actually written here. So you can use these, and then you can use the software with those. A high-level overview of what the software is doing is this. TVB needs some input data, and this input data has to be provided from somewhere. And as you've seen in the previous talk, the actual data that TVB consumes is not direct imaging data. You have to have a certain pipeline that produces connectivities and other more structured data from imaging. As you've seen in the previous talk, that can be quite a sophisticated thing. Through the lifetime of TVB, there were more ways of doing that, and we hope that we will find some way to document a more canonical way of doing it. But it's important to remember and to keep this in mind that TVB, the package, does not start with imaging data. It needs these connectomes. Okay. So going back at our application. After you start TVB, okay, now I want to talk about data in TVB. How does the TVB model data? Where does it store the data, and so on? For our local installation, TVB creates a folder in your home folder, in your user folder. It's called TVB. All the data that TVB creates and uses is going to be stored there. Don't delete that folder unless you want to just erase all your work with TVB. Then, TVB organizes data into projects. This is the high-level way of organizing data in TVB. By default, TVB comes with a project that contains enough of these input data types so that you can usefully play with the software. So it comes with enough data so that you don't require one of these processing pipelines just to start playing with TVB. So let's see that. I'm on this screen here, project, and here is the list of all the projects. And if I click there on the project data, I will see all the data types that are in this project. And as you can see here, there are lots of things, and these come with the default project. Now, if you want to import data into TVB, let's say you have actually run one of these pipelines and you want to bring the data into TVB, there is this columnar button here to the right. If you click that, you get a pop-up with all the data formats that TVB supports for input. I refer you to the documentation to see exactly all of these types, what they do. I won't go through all of them. But for instance, just as a short example, you can here import connectomes in, for instance, this format. And if you click there, you get an unsurprising UI where you can just upload your file that was produced by one of these pipelines. Anyway, this is how you import data into TVB. And here is all the data types that are available in this default project. One last aspect, if you click any one of these, you get a pop-up with lots of information about that particular data type. And in this tab here, visualizers, I tend to use this more than any one of these tabs here. You get links to various pages in TVB which are able to visualize that particular data type. These are quite useful so that you can get an overview of how that data actually looks. Depending on the data type, you will have different visualizations. So here, or even more, for instance, for this particular data type, you have two ways of viewing it. Okay. So to summarize, TVB doesn't directly use imaging data. It needs imaging data to be preprocessed by a pipeline. Then what TVB does, it takes that data, and through simulation, it produces time series, various type of time series that it can then analyze and see, answer your research questions with that. And on the data organization aspect, TVB organizes data into projects, and these projects contain particular data types. Okay. I will now let Paula show you more about how to navigate this interface, and in particular, show you how to visualize connectons in TVB and even manipulate them. So here we go.
Thanks. So as you have already seen, TVB provides lots of pages. In order to navigate, to switch between them, we will need to use navigators and menus. The main navigator is this one, placed on the bottom of the page. And this will hold 6 categories with which we can work. The most important ones are the project, which provides access to all our project data, as Mihai has previously shown. The simulator, where you can configure simulations and launch them and check the results. And also the connectivity, which is offering different ways of inspecting and manipulating a connectome. So I will go further inside the connectivity category because I like to give you more details about it. So I just go on the bottom navigator and click on it. Now, as you can see, a second level navigator is being displayed. This one provides a list with all the pages available for the current category. So for the connectivity, we can work with these 3 pages. I will choose the large-scale connectivity. An important aspect is that for some of the pages, CVB will require you to give an input. So in our case, we want to go ahead and visualize a connectivity. And TVB will ask which connectivity we want to visualize. We can select the connectivity we want from this list and move forward by using this right side button. Now here we have the large-scale connectivity page. You have seen it before. Be aware that from here we still have access to all the navigators. The bottom one is always shown, and the other one is accessible from this button. Another important button in TVB is this top right corner one. Now, what does this do? This provides a list with settings that we can apply to the visualizers within the current page. Some of these visualizers will have immediate effect. Some of these settings will have immediate effect upon the visualizers. And for example, we can choose another color scheme. We search the one we want inside this list and just select it. And as you can see, the color changes accordingly immediately. On the other hand, we also have settings that do not have immediate effect, but require an extra user input. And as an example, inside the left side 3D viewer, I can show a brain surface. In order to do that, I go to this field, choose the surface I want. As you can see, nothing happens until I click this update button. Okay. So the page is refreshed. We see our color scheme remained the same, and the surface appears on the 3D viewer. Okay. Besides the page layout, I would also like to give you more details about what you can do inside this connectivity page. First, I would like to remind you that a connectivity in TVB will define the global behavior of the brain model. It will describe how the strengths of the connections and also how long these connections are. What do we see here? On the right side, we will see a metric structure with information about the strengths of the connections and also about the length of the connections. We can also check the region names, which are displayed here as the matrix headers. Okay? As connectivities can be quite large in TVB, we are splitting them in 4 quadrants. And what we see here are information about the connections between the nodes of only the left hemisphere. If you check the matrix headers, we have left per left regions. In order to check the other quadrants, we need to use this selection and switch between them. For example, if I go on the 4th quadrant, I can check the strength of the connections between the right hemisphere nodes. So right per right. If I want to see the interhemispherical ones, I go to the 2nd or the 3rd quadrant. Okay. On the left side, we can see the 3D representation of those nodes. What is useful here is the fact that you can right-click on a node and check local information about it. So you will see the region name, and you can also draw connections it has with the other nodes. You can inspect the connections, and besides showing only the local ones, you can also inspect the entire global connection. If you click on this button, you'll see that all the connections are displayed here. Okay. Besides inspecting information about the connectivity, within this page, you can also manipulate it. Now, a common way of manipulating the connectivity would be to cut out some of the connections. And to exemplify this, I would like to show you how we can cut out all the connections between the 2 hemispheres. Okay? You can see here that the hemispheres are connecting through these edges. And our goal would be to cut them out. Now, in order to do that, we will need 2 steps. First, we need to select all the nodes from a single region, a single hemisphere, sorry. So how do we do this kind of selections in TVB? We have 3 ways. The most straightforward one is to just go here and click on region names. As you can see, the selected regions are shown in green, and once I unselect a region, it is shown in white. By clicking here, I can toggle the selection, select and unselect them as I like. This is fast and useful for if we are trying to select few nodes. But when we are trying to work with larger groups of nodes, like selecting an entire hemisphere, as we need, TVB has smarter ways. One of them is this pop-up. This is more advanced, and it will let us, for example, select and unselect all the regions at once. Also, we can manually select some of the regions we want, and in order to later use them in TVB, we can save this group of nodes, group of selected nodes, as a selection. We can just give them a name here and click on the Save button. We'll see that the selection is shown in this list, and we can use it later in other TVB pages. Okay, but we want to select the nodes of an entire hemisphere. We can do that here by going manually on each region and selecting it. It is totally fine. But there is a quicker way to do it for our use case. So just leave them all selected for now and use the 3rd selection way TVB provides. Here we have a list with all the selected regions. And in order to leave only one hemisphere selected, we can just erase all the labels corresponding to nodes from the right hemisphere. We select them, we delete them, and apply the changes. Okay? In order to verify the result, we can see now that only one hemisphere is left selected, and the other one is not. Okay, so we have the first step. We have selected an entire hemisphere. Now, let's get to actually cutting those interhemispherical edges. What does that mean? That means that we have to modify the strength of the connections between the two hemispheres to a value of 0. In order to do that in TVB, we use this edge operations menu. This allows me to set a 0 value on the connections that start inside the selected set of nodes and end in the unselected set of nodes. And I can apply this 0 strength value on them. But as in TVB, the connections are bidirectional, I have to do this again. So set a 0 value for the strength of the connections, but this time the connections that go from the unselected set of nodes towards the selected one. So the out-in type. And I can also apply this with this button. Okay, in order to check the result, I have to refresh the 3D viewer and show again the connections. As you can see now, we no longer have any connection between these two hemispheres. Okay, that's one way to manipulate a connectivity. And once I have obtained the new connectivity I want, I can save it and use it later in TVB for simulations, maybe, by giving it a name here and clicking this Save button. As a result, this operation will save my new connectivity as a data type inside my current project. And I can always access it from there. I think that's all for this connectivity page. And I will let Mihai introduce you to the simulator.
Yep.
Yeah, so 2 questions. So right now, the goal was to cut between the 2 hemispheres.
Yep.
Okay, so but you selected all the left nodes, right? And then you said cut all incoming and outgoing connections.
Yes.
Why did it not cut also the connections within the hemisphere?
The way to actually read what that menu is doing is the following. Perform this operation for all the edges that connect the selected and the unselected set.
To the selected and to the unselected?
No. All the connections that start in the selected set and end in the unselected set. So, and with these connections, perform this particular type of operation.
And that's the set N, or what is it called?
Yeah, it's called the set operation. There are more there, but the set operation is the one which works here. As you've seen there, you also have like in that menu, there is also that option from in to in. What that means is perform this operation on all the edges that connect between the ones in the selected set. Or out to out is perform this operation. For instance, let's say I want to upscale the strengths of all the connections in the left hemisphere. Then I will set multiply operation from in to in by 2. Okay, it is was not so simple operation, but it's quite powerful, and I hope. Did everyone understand what the semantics of that is? Yeah.
And here in this weights matrix, if you look at the connections from left A1 to left A1, for example, and then you look from left emitter to right emitter, but then later it's not always the same value on the diagonal of the matrix.
It is not. No.
Why is it that the connections to one is really a value? I mean,
On the main diagonal.
it seems to have variance there. I would think that connection to itself would be a non-inflammatory value.
It is. It is. It is.
And what does it represent in that case?
Uh,
To itself, so connection strength to itself.
yeah, it should be an influence on itself.
And that is also derived from DTI or from...
I'm not so sure. I will refer this question to other people.
This is coming from the default connectivity matrix. Default connectivity matrix is coming from CocoMac, which is a database that was put together by a colleague in Düsseldorf many years ago. So this is not based on DTI, it's based on a monkey database called CocoMac.
From a purely mathematical point of view, it could make sense to have self-connections because you have delays. So you would say, I can be influenced by my previous state as it was how many steps ago. So,
sorry, I'm a little confused, but is this structural data?
yes.
How come it's asymmetrical?
Again, in the CocoMac
I-
database, it has directionality information. So that's
Excellent pricing studies.
Mm-hmm.
Much the human DTI data.
Yeah, I'm just trying to picture how because it tracks, right?
right. So if you actually do injections into the brain,
Oh my God.
this is actually chemical tracing, track tracing, not DTI.
With dyes, when they inject dyes. Okay. Or you can see this as an extra feature that the TVB simulator is actually providing you. You can definitely use symmetric matrices here. But if you want to model this kind of asymmetry, you can. And in the default data set, there is this asymmetry. For the weights, for the distances, I don't think it makes much sense, and this one is symmetrical. The distances between the nodes. So the connection strengths might differ depending on the direction that you take, but the distances are symmetrical. I've never seen an asymmetrical tracks one, but yeah, I'm a software guy, so many of these scientific questions I have to defer to other people. Okay, any other questions about this? Okay, then I can move on to the simulator. You can access it from here, the big simulator button. But before discussing about simulations, I want to show you a different page, a page where you can actually explore how the local dynamical model behaves. So if in TVB, connectomes describe this large-scale structure, models describe the local structure, how a particular node behaves. Randy already showed you some of these phase plots. These are quite nice tools to explore how these local models behave. In this page, which I reached by clicking simulator and then in the second level navigation clicking faceplane, on this page you can explore the models. Here, just on the left side, there you can choose what particular model you want to explore. And here on the right is a faceplane view for that model. I don't know how many of you are familiar with this kind of visualization. I think you are. So here are the state variables of the system, and the arrows show the tendency towards a new state. If it's here, it will tend to go there, and so on. The colored curves are null lines for this system. So the green one, if you start here, the system will have a tendency of moving horizontally and not going into this direction, and with this other north line, the other way around. What's useful here is that if you click on any of the points in this phase space, you will get a trajectory. This is a small, you can see it as a very small simulation of what this particular isolated model would do if it would start in that particular initial condition. If the trajectories are too small, you can make them longer by going to these viewer settings. And here is this integration step slider. I can increase that, and then I get a longer trajectory. And if I want to make it even longer, there is here an integrator section that dictates how these trajectories are actually computed, and I can increase this integration step. Where's the dot on this keyboard? Yeah. Good. So now the trajectories are more informative. I can click around to have more trajectories and get a feel of how this model would behave. So in this particular case, this model will attenuate any kind of initial conditions. So it will just oscillate and in the end die out the signal. Now, all the models in TVB have configurable parameters, and all of the parameters that are configurable you will see here in this section. Yep.
The integration step is the steps between iterations of the integrator, or the span time that you...
It's the steps between, the time between the steps of the integrator. Yep.
And the slider down is the duration?
This is the duration of the simulation. So if you can get away with just increasing the steps of the simulation to the maximum value that is here, then do that. But if you want even longer trajectories, you will have to increase the integration step. We don't provide here arbitrarily large integration steps because then you would click here and you will have to wait for a long time for the trajectory to be computed, which is against the purpose of this page, to give you a quick overview. This is not to actually run the simulation. Just to give you a quick feel of how the dynamics of the model, how the model behaves. So as I briefly mentioned before, models have configurable parameters. And on this page, you can see what these parameters actually do to the behavior of the model. For instance, in this model, if I increase this particular parameter, the A parameter, as I increase it, you see that the time that it takes for these oscillations to die out increases. And more interesting, if I make this parameter large enough, I've reached a bifurcation, and now the model behaves completely different. So from all of the initial conditions, now I don't go to a fixed point, I go to a limit cycle, and it will forever make these oscillatory signals. Okay, so here you can play with all the parameters and see what kind of signals that particular parameter configuration of a model will give you. Underneath the model, you have a time series for the state variables of the last trajectory that you've clicked. So if you want to have also a view of how the signals would actually look in the time space and not in the phase space, this is also a quick, useful visualization. Good. So once you found some interesting parameter configurations, some interesting dynamics, you might want to save these things. For that, you write here a name. For instance, this is some kind of oscillatory stuff. And then you click here to save this parameter configuration, and then you can use this configuration of parameters in simulations later. I will not show you how to do that. Paula will. But this is quite a useful feature. You've found a combination of parameters that gives you some interesting dynamics, and you save that, and you can use that later with the name that you've given there. Another thing that you might want to explore here is to see how would the model behave when there is noise, integration noise. For that, in this viewer settings region, you can choose another type of integrator. So the default one is a deterministic one, which is quite useful to get a very clean view of what the dynamics are. If you choose another one, like stochastic Hoyne, you will see the dynamics of a noisy version. This one is definitely completely dominated by noise. So I will have then to explain what some of the parameters of these integrators do. Even though it's a bit buried, this D parameter is the dispersion of the noise. So in this case, I will have to significantly decrease this one from the default to a more sane value. This is way too little. Make the integration step a bit larger. Anyway, yeah, and here you see how the model would behave if there is noise present. Okay. So this is another thing that I wanted to tell you about here. This particular model is two-dimensional, but most of the models in TVB are actually higher dimensional, and there are some complications there. How do you see the dynamics of a multidimensional model? There are here options that allow you to do that. It essentially restricts the dynamics to two state variables, but I won't go too much into detail about that. I refer you to the documentation, but this can also be used to explore the dynamics of more multidimensional models by essentially choosing what kind of combination of two state variables you want to explore. Okay, any questions about this? Okay, good. Then I will go on to show you the simulator of TVB. The most sophisticated page, I think, in TVB, but I will help you navigate it. It is split in these three columns. On the left, you have a history of all the simulations that you have run. If you click on them, you can then load the results of the simulation and so on. In the middle is this column where you can configure a new simulation, and to the right are some previews. Once you've run a simulation, you will see here just short previews of what the time series that were produced look like. So let's configure a new simulation. You can click here to create a new one. There is already a new one here. And in all of these fields have a natural story. First, you configure this large-scale structure. You begin by selecting a connectome here. Then by choosing this a coupling function. Which coupling function to choose depends on which model you're choosing. And you will have to read the paper that comes with the model to learn what kind of coupling do you need there. If you want a quick reminder, there are these green buttons here. If you click on them, you will find short help and even links towards the papers where you can read more about the models and about these particular coupling functions. Just to say a short word about what they are doing, they are dictating how the signals actually propagate on these connections, what kind of transformation occurs on these edges. What they all have in common is a kind of strength parameter. They are also parameterized. In the case of this linear coupling function, this A parameter establishes how strong the connections are. So if this one is small, the nodes in your connectivity will behave as if they were isolated. As you increase that, the whole network becomes increasingly tightly coupled. One last interesting global parameter is the conduction speed. That's here, and it's obvious what it does. You say how fast the signals should travel through the tracts of your network. Okay, once you've configured these global parameters, then you have to choose one local model from here. These are all the models that you've seen before in the dropdown in the phase plane. And underneath this, you have all the configurable parameters for this particular model. You can use here the configurations that you've saved earlier, and Paula will show you how you can do that. Otherwise, you can just, for instance, click here, get some information about this particular model, go read the paper, and fill in here the values that you've copied from the paper, or play with your own assumptions and so on. Okay. So we've chosen the global structure. We've chosen a local model. Then there is this integration scheme. Here you can make the decision of whether you want noise or deterministic simulations. That's the first decision that you can make there. Then there is this integration step size. We can't isolate you from that. The smaller it is, the longer the simulation takes, but it is safer to have it small. If you increase it, you will have quicker simulations, but you might diverge. We also have a whole collection of integration schemes here. If you can go to the documentation and see what the advantages and disadvantages are of each one of those. If you are familiar with simulation and dynamical systems, I think you will find many of them familiar of these integrator schemes. But if you don't want to study much about ways of choosing integration schemes, we recommend these Hein integrators for now. And then you basically just have to choose whether you want the deterministic one, the Hein, or the stochastic one. For the stochastic one, as you've seen in the faceplane, you almost always have to make a decision on the noise dispersion. The default is intentionally large. So you have to make a decision about that. If you click on choosing, for instance, the stochastic one, you have here lots of options, but this is the one that you will have to change, the dispersion of the noise. Okay, finally, you have to choose what kind of output you want. By default, you get as an output a time average of the local potentials. Or to be more precise, you get a time average of the state variables of the system by default. But you can also ask TVB to produce EEG, MEG, or bold data. For these different kind of signals, like EEG, you will have to provide more data types for TVB. If you want EEG, you have to tell TVB what kind of head model do you have, where the sensors are, and so on. Okay, and finally, how long do you want your simulation to be? You give the length of your simulation and give it a name so that you remember what the simulation is supposed to do. Click Run. Let's actually give this one a name and run it. Make it unnaturally short so that it finishes while we talk. Okay. TVB runs the simulations asynchronously because it takes a while. Just a second. This is intentionally short, but realistic simulations take a long time. They run asynchronously. While they run, you can still use TVB, even launch new simulations. Here in the top left corner, there is this button, which is an overview of the asynchronously running operations. I don't think you can read it so well, but if you click there, it will be obvious what it shows. It shows how many operations have finished, how many operations are still running, and so on. Can I have your question?
So many of these variables have this expand range button?
Yeah.
So can we set an interval to run multiple simulations?
I'm about to say that. So because for many of these parameters, there isn't an obvious value to pick, you would actually want to see how a collection of parameters would look. How would the simulations look if you would increasingly make the coupling of the network larger? So for that, you have these expand range buttons. Going back to these long-range coupling functions. Let's say I want to start with an almost decoupled network and then increasingly couple it to see what happens. I expect when it's completely decoupled to behave as if I were into the phase plane. All the nodes are behaving independently as the dynamics dictate. If I increase the coupling, everything will get more correlated and maybe even completely diverge if there's very strong coupling between them. So I would click here this expand range button, and you have here a small UI that allows you to define a range for that parameter. If you've done that, while you do that, pay attention that at the top right corner, you have an information of how many simulations will this range actually launch. Don't run hundreds of simulations unless you're really confident that you want that kind of precision, because it takes a while. And if you launch now this configuration where you have selected a range for a parameter, you will get what we call these parameter space explorations. They run one simulation per one for each one of those parameters. If you run that, you will get this kind of output here to the right. And in this case, I've varied two parameters. I varied here the coupling strength and the conduction speed. And you get one of these circles for each one of the simulations that were run. You can click on them and then see the time series. Let's actually do that. Click on this, and I get a pop-up for the data type that was produced. I can go to visualizers and pick one of these visualizers and actually have a look at the signals. Okay. This was mostly it. Another thing that might be useful for simulations that are not these parameter sweeps, you can see here a preview after they're run. And if you click this maximize button, you are going to see a full visualizer with the signals. And here to the right, you have this selection screen that you have already seen in the Connectome page. And here I can even choose the selection that she made, like choose all the left hemispherical signals and so on. Okay.
How do you reset that now? If you change something on the left, how do you rerun it? So the play button disappeared now, right?
Yes. The play button disappeared, and we have that branching button. That is meant to be used when you've done a simulation and you want to continue it. Like, I've simulated 3 seconds. Okay, I like what I see. I want now that simulation to be continued for another, I don't know how many seconds. If you want to run a simulation which is almost like another one that you've just run, in the history side to the left, if you click here, you have this copy button. It's a bit buried, I admit it, for a common use case. But you can go there, and if you click copy, you will get another screen here with all the configuration that was used to the previous simulation. So this does not copy the history of that simulation. The branching button does that. This only copies the configuration, and then here you can tweak the configuration and not just a similar simulation.
So you cannot really like update the view. You have to always create a new simulation if you want to play around with things.
What kind of playing around with things do you have in mind?
You know, I wanted to, if I change the parameter on the left, the values on the right don't change.
No, because you have to run a whole simulation for that.
I know, but I cannot just, say, now update the curves on the right.
No, you will have to copy the configuration for the simulation and to run another one. There is actually a reason to that besides, every feature implies some software development. But simulations take a while. They are these asynchronously running things, and they don't go that well with this kind of interaction that you intend to be immediate. When you change a parameter and you say, I just focus out and I want the thing to update, you don't expect something that might take 3 hours to run. Yep? Yeah, I will talk about this a bit later. But now I want to let Paula show you how to configure this particular model configurations in space. to say this particular node has this particular behavior, this particular node has a different behavior. You can do that in TVB. So I've spoken enough.
As Mihai has shown you, inside the faceplane, we can configure parameters of the models. And he also saved some of them, and I will show you how to use those. In TVB, we can choose different model configurations for different nodes. Where we do that, from this simulation page, we just click on the Setup Region Model. Okay, we have here an overview with all the regions, and they are all selected by default. Now let's say I want to apply a model configuration on all of them. Using this field, I can access all the model configurations saved within the faceplane. So I choose the one I want to apply by clicking on it and apply it to all the selected regions using this button. Okay? I can verify that my operation is correct by going through this green model configuration names. Maybe you didn't save the model configuration. You have to give it a name inside the faceplane and then click some button here to save it. Okay. Now, all my nodes will behave similarly. But I want, for example, these two to behave differently. And in order to do that, I just select them manually and choose the other model configuration and apply it on them. Okay? Again, I can verify the overview, see that all of the nodes behave in this way, except the two ones which behave as the subthreshold model configuration defines. Okay, in order to use this local behavior configuration on my simulations, I will have to submit the region parameters using this button. Okay, as Mihai has shown you, here is where you can configure your local dynamic models. And as a result of the configuration we just did, we can see now that instead of having a single value for all the regions here, we have a different value, an array with different values for each of the regions. Good. So similarly to defining those local models on TVB, we can also define stimulus on a node. In order to do that, we will need to work with this stimulus category. Okay, we choose it and go further with the region stimulus page. This will also work in two steps. And the first one is defining the actual stimulus. This stimulus can be defined here. And as you can see, we have the representation of its waveform. What we can configure for it is first the connectivity on which we want to apply the stimulus and an equation. We can choose between this list of equations. We will see all of the waveforms here. We will choose the one we want. And afterwards, we can also variate the parameters and define the waveform as we like it. For example, we just introduce some values for these parameters and get a new waveform. Okay. Once I have defined the stimulus I need, the second step is to actually apply the stimulus on nodes. how to do that, I need to use this button, Set Region Scaling. What do we see here? We again have an overview with all the regions, and near each region we see a 0 value. This 0 value means that we have no stimulus applied on that region, so no stimulus applied on this connectivity. If I want to apply a stimulus on, let's say, this node, I just select them, use this field to give a value, for example, 1, and set it on those nodes. Okay. As a result, we will have all of these nodes with no stimulus applied except these 4 ones, which will be influenced by the stimulus we have previously defined. Now, in order to save this, we'll have to give it a name here and save it using this button. This again, as a result, will create a new data type inside the project, which we can later access and use in TVB.
So everything you're saving is that project specific?
Yes.
So if I start a new project, I have to re-input everything, or can I transfer stuff?
You can transfer.
You can import things from one project to another. You can link between projects.
Okay. I think that's about it with the web interface. Basics, of course. You can do a lot of things in TVB. And I will let Mihai introduce you to another way to interact with TVB.
Yeah. There is this field there that establishes the scaling factor of that stimulus in that particular, in that selection. So you select a family of nodes, then you go there, input some kind of value, and set scaling. You will have the opportunity of actually playing with the software shortly after we've done. We have this workshop, so don't focus too much on trying to reproduce what we've sent. I actually should have said this in the beginning, not now that I'm about to finish. Sorry about that.
One question for the stimulus, is it considered to represent more magnetic or electric stimulation, or how is it defined?
I will have to refer this question to somebody else. From TVB software standpoint, it's influencing the couple variables. So.
Another presentation later today on this topic.
Yeah. Okay, so just briefly, this is the graphical user interface is a nice way of interacting with the software. It's more discoverable. You have this visual memory of what you've done. But TVB also offers a different interface. If you're familiar with scripting, you used MATLAB or even Python, you can use TVB as a library, as a Python library. This has 2 advantages. If you create a script, that's really reproducible, what you've done. The pattern of clicking through the UI is not so reproducible and distributable. Another advantage is that you have the full power of the API. The graphical user interface cannot expose all the functionality that the libraries actually provide. If you want some very specific things, you will have to use TVB as a library. Of course, the disadvantage is that you will have to learn that API and also always have this documentation nearby and see what happens. And that being said, let me show you how to start that. So going back to where you've downloaded TVB in one of those distribution folders, I have mine here. There is a bin directory, and that bin directory contains more commands there. There is one command called IPython notebook. Just run that. After you've run that, you get this page. If you're familiar with Jupyter, you already know what this is. Otherwise, it's kind of similar to MATLAB. You have here different scripts. And if you click one of these, the script looks like this. It has these cells. It either has documentation or code. And the ones that you see by default are small tutorials about how to actually use this kind of interface. And here there is code that describes how to run simulations using the API. It parallels the UI in many ways. You start by choosing a connectome, you configure a simulator, and so on. I won't go into details about this, just know that it's there, and it can be the tool that is more useful for than the GUI in particular use cases. Okay, this being said, thanks for your attention. There will be workshops and more talks that will use TVB more motivated by scientific problems. And I hope you will enjoy working with TVB. Let us know if you start working with it. Let us know if you find bugs. Or if, for instance, some aspect is not documented in the UI, in our documentation, ask us to document things as well. Yep.
Do you accept pull requests?
Yes, we do. So our code is on GitHub. We welcome any contributions. So we do. And just get in touch with us so that we can help with that. It's not a small piece of software. So you might need some guidance. Yeah.
I also discovered the MATLAB folder. Is that an interface for MATLAB, or does it use some MATLAB code, or what is that for?
Yeah, both. TVB can interface with some scripts written in MATLAB mainly for analysis. And also TVB can, the library part of TVB can to some extent be used from MATLAB. It's not a use case that we support very much. Okay, thank you for your attention.